Hi everybody, I am Dr. D. MABUNI, Assistant Professor, Department of Computer Science, Boolean University, Kuppam, Andhra Pradesh, India. Information retrieval subject is offered to MCA 5th semester students of the Department of Computer Science, Boolean University, Kuppam, India. The prescribed books for this subject are 1. Introduction to Information Retrieval by Christopher D. Manning and by others. Second one, Natural Language Processing and Information Retrieval by Tanveer Siddiqui and U.S. Tiwari. The first unit is about Boolean Retrieval. Through this video, I will share some basic information about Boolean Retrieval, which is a subtopic of the field information retrieval. Information retrieval is the field of computer science that deals with the processing of documents containing free text so that they can be rapidly retrieved based on keywords specified in a user's query. The Boolean retrieval model is a model for information retrieval in which we can, we can pose any query which is in the form of a Boolean expression of terms, that is, in which terms are combined with the operators and, or, and not. Example, Brutus and Caesar and not Calpurnia. That is, user wants to retrieve documents which contain the terms Brutus and Caesar and not Calpurnia. According to the prescribed textbook, the definition of information retrieval is as mentioned here. Information retrieval IR is finding material, usually documents of an unstructured nature, usually text that satisfies an information need from within large collections, usually stored on computers. Many of us think that information retrieval means web search, but there are many cases in which information is retrieved. Some examples are email search, searching your laptop, searching corporate knowledge bases, legal information retrieval. The term unstructured data refers to data that does not have clear, semantically overt, easy for a computer structure. It is the opposite of structured data, the canonical example of which is a relational database of the sort companies usually use to maintain product inventories and personal records. Basic assumptions of information retrieval. Collection. A set of documents. Assume it is a static collection for the moment. Goal. Retrieve documents with information that is relevant to the user's information need and helps the user complete a task. The classic search model. The classic search model is like this. A user needs information to complete his or her task. To get information, he or she submits a query to the search engine. The search engine retrieves the relevant information from the collection of documents and generates result. If results are not specific, then the user refines the query and submits it to the search engine once again. This will continue until the user gets the required specific information so that he or she can complete his or her task. The second topic is an example information retrieval problem. A fat book that many people own is Shakespeare's collected works. Suppose we want to determine which plays of Shakespeare contain the words Brutus and Caesar and not Calpurnia. This diagram shows how an information retrieval system processes an user's query. The information retrieval system accepts the query submitted by a user. Example is Brutus and Caesar and not Calpurnia. The information retrieval system retrieves the plays that contain Brutus and Caesar and not Calpurnia. There are different ways to process a Boolean query. They are grepping, using a term document incidence matrix using an inverted index. Grepping. One way to retrieve information is to start at the beginning and to read through all the text, noting for each play whether it contains Brutus and Caesar and excluding it from consideration if it contains Calpurnia. The simplest form of document retrieval is for a computer to do this sort of linear scan through documents. This process is commonly referred to as grepping through text after the Unix command grep, which performs this process. Grepping through text can be a very effective process, especially given the speed of modern computers, and often allows useful possibilities for wildcard pattern matching through the use of regular expressions. Because of linearly scanning the documents, grepping takes much time to retrieve relevant documents. The following are the information retrieval requirements for many purposes. Number 1. To process large document collections quickly. The amount of online data has grown at least as quickly as the speed of computers, and we would now like to be able to search collections that total in the order of billions to trillions of words. Number 2. To allow more flexible matching operations. For example, it is impractical to perform the query Romans near countrymen with grep, where near might be defined as within 5 hours or within the same sentence. Number 3. To allow ranked retrieval. In many cases, you want the best answer to an information need among many documents that contain certain words. The second way of processing a Boolean query is using a term document incidence matrix. The way to avoid linearly scanning the text for each query is to index the documents in advance. Suppose we record for each document here a play of Shakespeare's, whether it contains each word out of all the words Shakespeare used. Shakespeare used about 32,000 incidence different words. The result is a binary term document incidence matrix, as in matrix shown in the figure 1.1. This figure 1.1 shows an example for a term document incidence matrix. In a term document incidence matrix, each column D represents a document play and each row represents a term T. If the document D contains the term T, then 1 is entered. Otherwise, 0 is entered. Now, depending on whether we look at the matrix rows or columns, we can have a vector for each term which shows the documents it appears in, or a vector for each document showing the terms that occur in it. Example query 1. Determine which place of Shakespeare contain the word Brutus. Solution. Take the vector of the term Brutus, that is 1 1 0 1 0 0. The answer for this query are thus Antony and Cleopatra, Julius Caesar and Hamlet. The ones complement or complement of a binary number is defined as the value obtained by inverting all the bits in the binary representation of the number. For example, one's complement of 0 is 1, one's complement of 1 is 0, and one's complement of 1010 is 0101, and one's complement of 1111 is 0000, and so on. Binary AND operation. The binary AND operation, also known as the binary AND function, will always produce a 1 output if both of its inputs are 1, and will produce a 0 output if one or both of its inputs are 0. If we call the inputs A and B and the output C, we can show the AND function as 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. This is the example for AND operation. Argument 1 is 0 0, 1 0, 0 1, 0 0. Argument 2 is 0 0, 1 0, 0 0, 0 1. The result of AND operation is 0 0, 1 0, 0 0, 0 0. Example query 2. To answer the query Brutus and Caesar and not Calpurnia, we take the vectors for Brutus, Caesar and Calpurnia, complement the last, and then do a bitwise AND operation as follows: 1 1 0 1 0 0 and 1 1 0 1 1 1 and 1 0 1 1 1 1. The result is 1 0 0 1 0 0. The answers for this query are thus Antony and Cleopatra and Hamlet, as shown in the following figure 1.2. These are the retrieved documents for the query Brutus and Caesar and not Calpurnia. These documents contain the terms Brutus and Caesar and do not contain the term Calpurnia. The third way of processing a Boolean query is using an inverted index. A term document matrix requires more computer's memory, but the crucial observation is that the matrix is extremely sparse, that is, it has few non-zero entries. A much better representation is to record only the things that do occur, that is, the one positions. This idea is central to the first major concept in information retrieval, the inverted index. Inverted index, or sometimes inverted file, has become the standard term in IR. The basic idea of an inverted index is shown in the following figure 1.3. This is the figure 1.3. According to this diagram, an inverted index is divided into two parts, that is, dictionary and postings. The dictionary contains all the terms. In postings, a postings list is created for each term. Each postings list contains document IDs of the documents which contain the term. For example, the term Brutus exists in 8 documents. We keep a dictionary of terms. Then for each term, we have a list that records which documents the term occurs in. Each item in the list which records that a term appeared in a document is conventionally called a posting. The list is then called a postings list or inverted list, and all the postings lists taken together are referred to as the postings. The dictionary in figure 1.3 has been sorted alphabetically, and each postings list is sorted by document ID. The third topic is building an inverted index. To gain the speed benefits of indexing at retrieval time, we have to build the index in advance. The major steps in this are as follows. The first step is collect the documents to be indexed. First document is friends, Romans, countrymen. Second document is so let it be with Caesar. The second step is tokenize the text, turning each document into a list of tokens. Friends, Romans, countrymen, so, let, and so on. The third step is do linguistic preprocessing, producing a list of normalized tokens, which are the indexing terms friend, Roman, countryman, so, and so on. Fourth step is index the documents that each term occurs in by creating an inverted index consisting of a dictionary and postings. The following figure 1.4 shows an example for building an inverted index. Building an inverted index by sorting and grouping. The sequence of terms in each document tagged by their document ID shown in left is sorted alphabetically shown in middle. Instances of the same term are then grouped by word and then by document ID. The terms and document IDs are then separated out, shown in right. The dictionary stores the terms and has a pointer to the postings list for each term. It commonly also stores other summary information such as here the document frequency of each term. We use this information for improving query time efficiency and for weighting in ranked retrieval models. Each postings list stores the list of documents in which a term occurs and may store other information such as the term frequency, that is, the frequency of each term in each document, or the position or positions of the term in each document. The fourth topic is processing Boolean queries. A Boolean query is a query which is in the form of a Boolean expression of terms, that is, in which terms are combined with the operators and, or, and not. For example, Brutus and Caesar and not Calpurnia. Boolean queries can be processed using an inverted index. Consider processing the simple conjunctive query, Brutus and Calpurnia. Solution using the inverted index partially shown in figure 1.3. Step A. Locate Brutus in the dictionary. Step B. Retrieve its postings list. Step C. Locate Calpurnia in the dictionary. Step D. Retrieve its postings list. Step E. Intersect the two postings list as shown in the following figure 1.5. This figure shows the results of the intersection of postings list for Brutus and Calpurnia. The resultant postings list contains two document IDs, that is 2 and 31. That means two documents whose IDs are 2 and 31 have the terms Brutus and Calpurnia. Thanks for watching my video. We will meet with another interesting video soon.